This morning we're going to have a special presentation on how to make microchips. And we always like to start with some interesting historical information about the microchip. The microchip was subsequently invented or discovered, as we like to say, which is a combination of invention and discovery. My students actually came up with that great term. I love the term, so we're going to use it from now on. Inscovery. It was discovered in 1947 by John Bardeen, Walter Brattain, and Bill Shockley. Actually, John Bardeen and Walter Brattain were the actual scientists. They were actually physical chemists, which is really cool. They weren't engineers. They were chemists, which gave them a tremendous amount of understanding, underlying understanding of the principles, as well as Bill Shockley, who was a physicist. They actually were the two who discovered and demonstrated a working transistor on December 16th in 1947 at Bell Labs. They subsequently, the three of them were awarded a Nobel Prize in Physics in 1956 for that contribution. The world has never been the same after that. It was probably one of the most significant contributions in the history of science in human history. The interesting thing is, though, many years ago, about 70 years ago, I was putting together this calendar that I wanted to put together as a tribute to all the great physicists and chemists and scientists. And I wanted to call it Microelectronics Timeline, which you see as part of the name. But what occurred to me was, they didn't just wake up one morning and invent this or discover this transistor. There was a lot of work that was done before that, and as Isaac Newton once said, if I seem to see further, it's because I stand on the shoulders of giants. And indeed, these three men did that as well. They stood on the shoulders of giants who made some dramatic, compelling, significant contributions long before they were even around. And so the question now is, how do I offer a tribute to these people under a microelectronics name and go back before them? So I threw in the little addition of the title, which says, from the electron's perspective, and this is where things really change. This is from the electron's perspective. And what that means basically is this. The electron's been around probably since the beginning of the universe. And it'll be around long after we're all gone. So what we really did as a species was just begin to exploit how we can control that electron in our lives. Now, they were controlling it before we were born, and they were controlling it before 1947. In fact, as far back as 1831, Michael Faraday was exploiting it when he discovered some amazing phenomenon that had to do with electromagnetic induction. And we'll talk about that tomorrow. But during the course of scientific discovery, there were lots of inventions and discoveries made. And so the fundamental premise is technology might evolve and might become aged and old, but the underlying principles upon which that technology is based never go away. They've been around since the beginning, and they will be around long after we're all gone. And that's the beauty of this technology. So you're going to see some principles today and some technologies today that have become outdated, but the underlying physical principles will never go away. So one of the first questions I like to ask myself is, if this was discovered in 1947 at Bell Labs by Bardeen, Brattain, and Shockley, what did we use before then? Well, it turns out we used a couple of interesting types of technology. Probably one of the earliest technology demonstrations was done by Ferdinand Braun in the early 1800s. He took a piece of wire and touched it to a piece of galena, which is basically a rock from the earth, and in itself is considered a semiconductor. He touched this piece of wire to the rock and discovered a very interesting phenomenon. He discovered that if he applied a voltage to it, and ran a current through it, that the current would only travel through in one direction. If you put a battery, which is all we had in the early 1800s, we had no motors and dynamos and things like that. We only had chemical-based batteries. That if you put a battery across it, he could observe a current running in one direction, but if you reverse the polarity of the battery, it blocked the current in the opposite direction. That was the first time the phenomenon of rectification was ever demonstrated. And in fact, that simple configuration is now referred to, and has always been referred to, as a cat's whisker. If you ever hear the term cat's whisker, if you ever make a cat's whisker radio, it's that simple phenomenon. The difference between what he did then and what we do now is we've come to use highly purified versions of the galena. And the big problem with galena at the time was it just simply wasn't a pure semiconductor. And we'll talk about semiconductors, where they lie on the periodic table of elements in just a minute. Following that, another big problem with the cast whisker was it was very unreliable. It was hard to hold that wire in place and get a good signal and have it work in a good rectification process. And so, not long after the discovery of the cast whisker, another major discovery was made, and that was of thermionic emission. It was discovered, and partly by Thomas Edison, that if you heat up certain metals, in fact most metals, they give off electrons. Sometimes they'll glow, and sometimes they give off electrons. And that process of giving off electrons is what's referred to as thermionic emission. So following the discovery, or the discovery of the cast whisker, the vacuum tube was discovered and developed and invented. And a vacuum tube basically looks like this. These are vacuum tubes. These are many, many different kinds of big vacuum tubes. And these actually were used for decades. There was a huge industry built around vacuum tubes. And this is just like a light bulb. It's no different than a light bulb. It's got a vacuum. If you drop it, it'll break. But it works on a very simple principle. You heat up a filament inside, you create thermionic emission, forcing electrons to be forced from this. Then you attract them to another grid with a very high voltage. And you can control the flow of electrons from the filament to the grid with an intermediate grid, or to the plate we call it, the anode. And so by controlling the flow of electrons, we can generate and control all kinds of levels of amplification. So what I'm going to have you guys do this morning, we're going to actually turn one of these on. And I'm going to have you guys come up here, and I'm going to show you how to do that. So you guys make your way up here and gather around here, and we're actually going to turn one of these vacuum tubes on. So what we have here, basically vacuum tubes in the old days, if you look at this is an RCA vacuum tube, electron tube, and it's got a part number on it somewhere. Most of these have a part number. And these are often, so you have to do two things. You have to turn the filament on, and it'll glow. Once the filament's glowing, then you apply a high voltage and you begin to attract the electrons with that high voltage. We're not going to do the high voltage part. We're just going to do the filament emission part. And you also notice a silvery material painted or coated on the inside of these tubes. This is called a Gehry material. And what this was, as these were developed, we had to remove the air from these, just like a light bulb. But in order to pull out as much air as we could, because we wanted to create as much of a vacuum as we could, we applied this Gehry material on the inside of the glass, and then we'd flash it with a high voltage, or a high temperature. And what it would do is it would ignite, and by igniting it would then consume any residual amounts of gas or oxygen in the tube, and thereby enhance the reliability and performance of the tube. Now, these are big tubes, and we can turn these on. In fact, let's turn this one on. I'm going to assume the voltages that we use to turn on the filament is either 6 or 12 volts. Now, I have a transformer here that when I plug in, it's going to produce a certain voltage out here. And I'm going to ask you guys if you can tell me what that voltage is, so you know how to read a transformer. Well, if you look at the face of the transformer at the very bottom, you'll see input voltage and an output voltage. What's the output voltage say? 12 volt AC. See it at the very bottom? 12 volt AC. So that's the voltage on the very bottom. That's the voltage that we're going to get on the output of this. So it's a 12 volt source. Now, as I said, most vacuum tubes, filaments are energized either with a 6 or 12 volt. So we have to be careful we don't apply 12 volt to a 6 volt filament. So what we're going to do is, let's just try this one. I don't know what the voltage requirement of this is, but we'll know real quick. Because when we put these wires on it, it'll glow. It's either going to glow really bright immediately, which means it's probably a 6 volt filament, or it'll come up slowly. And it gives us a really beautiful, quiet, serene, almost like a flame. It's a beautiful, beautiful color. So the first thing we have to do is figure out which pins we're going to put the voltage across. And it's just like a light bulb. You just got to put the 2 pins across two of the wires. So what we're going to do is we're going to pull off. Let's use these because we can attach them like that. So we're going to take and we're going to put one here. And because it's AC, the polarity is not an issue. We don't care. In fact, it can be AC or DC. We can light the filament up with either AC or DC. All right, so I'm going to use 2 greens. You can use whatever color you want as long as you keep track of them. And in this case, because the polarity is insignificant, irrelevant, we don't really care. The trick is to figure out which 2 leads we're going to connect those wires to. Now, what I'll tell you is the filament is just like a filament in a light bulb. It's just like a resistor. It's just like a standard resistor. It's a component. It's got a certain resistance to it. And so we can if we have a meter, this is a little resistor, solid resistor. If we put a meter across the 2 light leads, we're going to get a resistance reading. And they're the only 2 leads that have a resistance reading. So we need some way of measuring resistance, and we just so happen to have, we have two multimeters here. We're going to use one of these multimeters. Now, the difference is in the kind of probes we have. This one has point probes, which are good to use, but not in this case because it's going to be hard to hold those probes on those pins. The other one has little clip probes, where you can actually clip them on the pin. So we could actually clip that to the pin. And we're going to do that. We're going to actually just find the 2 pins. I'm going to have one of you guys hold this. Ruben, you want to hold that? Just hold it upside down. And I'm going to have somebody else. Lydia, why don't you come in? I'm going to put this on resistance. And when we put it on resistance, push the clip out. We always double check to make sure it should say 0. Okay, so we're in the right mode and everything's working. Now what we have to do is we have to just walk around. So let's kind of do an organized thing. I'll start here at pin 1, right there, and you just walk around and touch each one until we get a reading of 0 or a low reading. It doesn't necessarily have to be 0. So just go to the next one. It'll read right away. Next, just go next. 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 Okay, we haven't found it yet. I'm going to give you a little hint. It's often pins 3 and 4. Typically pins 3 and 4. Is that right? Yeah. So let's go to pins 3 and 4. I think it's those 2. All right, hold on there. Move over 1 pin. Maybe it's 4 and 5. Nope, it's not those either. All right, well let's back up here. Now try that one. There you go. And then go from there. We'll just do it until we find the 2 that show a small resistance. Okay, try these. All right, start from there. You go. Just go all the way around. Does anybody else want to try it? And what Daniel's doing, because we haven't found it yet. Okay, start the next one. You see what we're doing? Yeah. We're literally trying every single combination that there is until we find a low resistance reading, and that'll give us our filament. Okay, go to the next one. Next. And go to 1. Did we do 1? Oh yeah, we must have done a 1 already. All right, we're not there yet, so let me go here. Try it now. Nope. Nope. Better be this pair, or else we're out of luck. Ah! See it? It is in fact the last pair. Wouldn't you know it, right? That's pretty cool. And let's see which pins that are according to the number system. Can you see which numbers those are? That one, 8? 7. Oh wow, that's kind of bizarre. All right, so we're going to connect these. Go ahead. Who wants to do this? Tristan, you want to try it, or anyone? Connect these to 7 and 8, which are these 2. Just clip them on. Just bite it like an alligator, straight on. There you go. Yep, just like it's going in the mouth. All right, and that where was I? All right, and then this one next to it. And we got to be careful; these don't touch. That's why we have the plastic little caps on them. That's it. Just right on down. Perfect. Awesome. Okay. Then all we got to do now is plug this in. But before we do that, Carl, you want to go turn the light off? Because it's a really pretty thing to see when this thing starts to glow. Okay? And all I'm going to do is just plug this transformer in. It's a transformer, by the way. We give microfarad credit for this. It's 100, converts 110 volt AC RMS to 24 volt AC, just like you saw. I'm going to stick it right in here, and let's see if we can turn this sucker on. We've had trouble with this thing before. See it? You see it? There it goes. And there it is. It's glowing. That's exactly what they look like. Can you imagine now a bed of these, which is what we used to build TVs and radios from? A huge bed of these. And in a minute, this is going to get really hot. They get really hot. In fact, they burn out. That's the problem. They weren't reliable. These were cool because they actually replaced the cat's whisker. That's why we use these. They replaced the cat's whisker because they were better and they lasted longer. Unfortunately, they didn't last much longer, but they lasted longer. And they were easy to manufacture and everybody could build them. And there's a beautiful, that's probably a 12 volt filament, which is exactly what you're seeing. And it's working. That's exactly how they work. There you go. There's your glowing vacuum tube. Now, the cool thing is, as I said, vacuum tubes come in all shapes and sizes. And we even have a lot of small ones here, which we could hook up the exact same way. And they would turn on and glow the exact same way as this one. In fact, these, I know for a fact, you connect the pins 4 and 5, or 3 and 4, or 4 and 5, one of those two pairs. This one's the, what's that? It's 4. Was it 4 and 5? Okay, Ruben remembers that. Excellent. And you can actually feel it's getting warm. You can, if you want to touch it, it's getting warm. It's not going to burn you, but it's definitely warming up. Yeah. And they will continue to warm. So guess what we had to do to cool them? Big, loud, noisy fans. That's all you heard all day long, these huge fans. And we had to cool them off. In fact, it wasn't uncommon to have them burn out maybe one every couple of days. The first big computer that used these, one of the first, was called ENIAC, built at the University of Pennsylvania. And it actually used about 18,000 of these. It was one of the first binary computers that we built and was using this as a switch. Before these were used, we used mechanical switches to control signals, binary signals, in a way that ultimately turned into the computer revolution. So there's a great picture of a vacuum tube, and as I said, these come in all shapes and sizes. We can actually light these up very, very easily. In fact, let's try that. Let's pull this off. You saw a little spark there. It's because I inadvertently touched the two leads. But if we carefully, if you hold this, let's see if we can light up. If you hold that like that. No, leave it off. We're good, because I want to show you glowing it. Who wants to hold that like that? Just hold it upside down, and I'm going to grab onto, let's see, pins 1, 2, 3, 4. This is actually going to be a little tricky because I'll run that all the way up. Okay, so what do I say? Where am I? 1, 2, 3, and Ruben, you said 4 and 5?
Yeah.
Okay, let's see if I can touch the pin 5 without getting a shock. No, I'm not going to get a shock. I just don't want to short them out. Oh, look at that! You see it?
Oh.
Okay, you can. That's a 6 volt. That's a 6 volt tube. Did you see it come on? I'll just hold it one more time. You see how fast it came on? There. See it?
Wait. So what are the vacuum tubes used for?
So the vacuum tubes are used for amplifiers.
Oh yeah.
Amplify low-level signals. That's exactly what they were used for. That was exactly what they were used for, was to amplify low-level signals. Because before this, we couldn't do it. We really couldn't do it. And until we had a way to do this, that really was the advent of the technology. Was to be, there it goes, was to be able to amplify very low-level signals. Pretty much is what we used the vacuum tubes for a long, long, long time. And in fact, televisions were used, these were used in televisions for decades. Okay, you can turn the light back on. So this was the technology for decades. And okay, you guys can take a seat. This was the technology for decades, and really up until around 1947 at Bell Labs. At that time, this changed everything. And what changed was we came up with literally an innovative new way, just a completely different way of amplifying low-level signals. And from that, the technology evolved rapidly and has been evolving rapidly for the past 60-some years. Now, what I'm going to talk to you about now is what exactly did they do? How did they do what they do, and upon what physical principles did they do it? And as you'll see, if I could turn this on, there we go. This was extraordinary. It wasn't necessarily entirely innovative because it had been attempted before. In fact, the catch whisker really was the first demonstration of what they ultimately demonstrated on December 16th of 1947. As a matter of fact, Bill Shockley attempted to demonstrate almost the exact same configuration almost 10 years earlier than this, and it failed. He even used a piece of germanium, which is what they used on December 16th, and it failed. And I'm going to ask you something. I think I may have asked you this earlier. What was it that changed in the 10 or so years from the demonstration that Bill Shockley tried with germanium and the demonstration that Bardeen and Brattain tried with germanium? Daniel?
They were able to purify the germanium?
Yeah, exactly. Tristan, is that what you were going to say?
Yeah.
They just basically were able to purify the germanium. And in fact, the purification processes that were developed actually during the Second World War, which is kind of a good thing. I'm not a big war advocate, but I love it when something comes out of a war that actually is beneficial to technology and to mankind, and this clearly was one of those cases. Would we have come up with that solution if we had not had a war? I don't know. I mean, I really don't know. I do know this: that the speed of evolution, the speed of technology, the speed of technology is non-linear, and it basically impacted and affected by things like in society, like wars and famine and disease and religion. Those things have impacted the evolution and growth of science from the beginning of time. And by the same token, we've had some very positive things come out of those very same reasons. The very same things that perturbated or may have slowed down progress, actually enhanced progress. And this clearly was one of the cases. In fact, many technologies came out of the Second World War, including one that we use every day in our lives, which is a microwave oven. The DC magnetron was invented in England in the early part of the Second World War, and it actually gave the British, an advantage in defeating the Germans during the Battle of Britain. So some amazing technologies came out, and clearly this was one of them. Well, let's look and see exactly what is this we're talking about? What is this technology? And how did it play into what took place on December 16th in 1947? So basically what Bardeen and Brattain were working with were semiconductor materials. And the semiconductor materials are a part of the group of elements on the periodic table of elements. And you've got three basic types of elements. You've got conductors, you've got insulators, and you've got semiconductors, which I call the temperamental elements. They don't conduct very well, but you can influence them to conduct in certain ways. And this is exactly what we did. And it starts off by understanding the most fundamental element that we use today, with which all microchips are made, and that is which element? Which element do we use to make all microchips from? Silicon, exactly. So we start with silicon, which has an atomic number of, remember the atomic number? 14. And it's got a unique melting point, which you should never forget after this lecture, which is 14 degrees Celsius. Now, silicon has one very unique property. It contains 4 electrons in its valence shell, as we talked about. And we know that the valence shell can hold a maximum of how many electrons? 8. So we have room for 4 more with silicon. And in fact, which is why silicon lattice is such a strong material, because the valence shells are filled in the covalent bonding. But what we learned from Bardeen and Brattain and what Shockley developed, they discovered that if you contaminate this element, silicon, with other elements, you get some very unique properties. And one of the most unique properties and functions occurs when you deliberately contaminate. We call it contaminate. The actual term is doping. When we deliberately dope the silicon atom with, let's say, a boron atom. Now, boron is an element that happens to have 3 valence electrons. In other words, 3 electrons in its valence shell. So if we combine silicon atom with the boron atom, how many electrons end up filling the valence shell? 7. Well, how many can we fit? So we have an excess of what? We have a space or a hole. We have a place available for an electron. And what we call that extra space or hole is a positive or p-type semiconductor. We dope it with boron, and it ends up creating the extra holes or extra spaces or vacancies for electrons. So we call this a p-type. Likewise, if we contaminate or dope the silicon atom with a phosphorus atom contains 5 valence electrons. Now if we contaminate the silicon atom with the phosphorus atom, 5 and 4 is how many? 9. Well, we have now an excess of electrons. So the excess of electrons is referred to as a negative dope, a negative type, or N-type doped silicon. So these are your 2 predominant types of combinations of silicon. It's either doped with boron or a phosphorus-type material, thus creating a P and N-type combination. And this is really where it all started. And what we discovered was some very unique properties. If you take a P-doped silicon and you interface it with an N-type silicon, you create what we call here a PN junction. And this is where all the magic takes place. Every microprocessor, every microchip on the planet Earth functions because of this phenomenon. Basically, by applying a voltage across this junction, what happens here is that you create a recombination of holes and electrons, or whole electron pairs. And by doing that, you're allowing current to flow. So you can induce current to flow in one direction. However, if you reverse the polarity of this battery and try to induce current in the other direction, it won't work because of the inability to recombine. And so it blocks current in this direction. Look what you just created. You've created a rectifier, or what we call a diode. This is exactly what Ferdinand Braun discovered in the early 1800s with a wire and a piece of galena. It's the very same exact property. It's just a lot more refined and much better to control and certainly easier to manufacture. Well, this basically becomes now the fundamental process with which all microchips on the planet Earth are made. And the function, let me show you what we're trying to get to. This is what we're trying to develop. I'm going to show you what we actually build, which will answer some of your questions that you asked yesterday. What we want to build, what we really want to build, and ultimately what we want to end up with is a switch. Just like the vacuum tube. We want to build a switch. And in fact, the silicon switch is the smallest switch ever created by man. A switch can be any size. Those fidget switches I showed you there, they're big, heavy mechanical switches. A light switch is a switch. It's no different than what we're talking about here. What controls? The switch typically has three leads. 1, 2, 3. It has a terminal on one side to connect something to, and a terminal on the other side to connect something to. But then something has to cause it to switch from one terminal to the other. With these fidget switches, what is it that forces that switch to switch from one terminal to the other? Yeah, it's you. It's your finger. It's your physical finger. A light switch is nothing different. What causes that light switch to switch from one terminal to the other? You. Again, a human. Well, in the microelectronics world, just like in the vacuum tube world, what we can use to switch from one terminal to the other is an electrical voltage. So the vacuum tube is very similar to a transistor switch. It's just not as small. And when I say small, I'm talking about sizes down in the nanometer range. 1 × 10⁻⁹ meters small. That's how small a solid state switch can be built as compared to a vacuum tube or a fidget switch or a light switch. And this is ultimately what it looks like in the physical world. The actual transistor that we're trying to build, and that's the name of the product that was invented in 1947. That was the first time that term had ever been used, transistor. And in fact, a poll had gone out through Bell Labs for people to come up with names for this new invention, and they got all kinds of crazy names, crazy words. You can imagine what these nerdy engineers came up with. Finally, one of them came up with the word transistor. Everyone liked that. And there's been some controversy over where that name came from. Some people think it was transfer resistor. There were different derivations of that. But suffice it to say, it became known and is still used today as a transistor. But here's what the transistor, I'm going to show you the symbol of the transistor that we use. And there's 2 types of transistors we're going to talk about. I'm going to show you the physical representation of that transistor. And this will answer a lot of the questions you asked yesterday, Danielle. And then we'll step back and look and see exactly how these are fabricated. How are they actually made? So the symbol, there's 2 kinds of switches. There are 2 kinds of transistors. There's what we call an N-type transistor, and there's what we call a P-type transistor. Now, this is a symbol. This is a schematic electrical symbol we use for those. But this is what the physical part, the actual fabricated part, really looks like. This is a silicon wafer. This is the surface of a silicon wafer, which we'll show you a little bit later. And then if this is the bottom of the wafer, it's not very thick. It's very, very thin, almost as thin as a piece of paper. But let's suffice to say we zoom in and look very closely at it. So this is a side view of a silicon wafer. And when we fabricate transistors, we do 4 fundamental things. Remember what those were? Did I tell you what those were? To this piece of silicon, this is a p-doped. By the way, it's p-doped. It's a p-doped silicon wafer, which is a round wafer, a very thin wafer, upon which we fabricate the microchips across the surface of the wafer. And when we fabricate these microchips, we do 4 fundamental things. We add stuff to the wafer. We remove stuff from the wafer. We grow stuff on the wafer. And we inject things, or we implant material under the surface of the wafer. And those are the 4 primary steps that we use to build every microchip ever built. And when we're done with a single microchip, a single transistor, it looks something like this. Now you notice there's three parts to this switch too, just like a light switch. This is called the drain, this is called the source, and this is called the gate. And this is a very special kind of transistor. It's called a field effect transistor because it operates on an electric field. This is an N-type, and this is a P-type. I'm going to show you the operation of an N-type transistor up here. Basically what we do is, as I said, we add stuff, we remove stuff, we grow stuff, and we implant stuff. What we do in this P-type silicon substrate is we're going to implant 2 N-type wells. We implant this using a very special implanting process. Then between the wells, we're going to grow an oxide. That's the grow part. Just like rust. You know what rust is. It's just iron oxide. Well, this is in fact silicon dioxide, a form of silicon dioxide. And this is our gate. So there's our source, or our source, our drain, and our gate. And this is the thickness I told you about yesterday, which is oftentimes only a few atoms thick. It's that oxide thickness right there. These have become so small that that thickness is oftentimes nothing thicker than a few atoms thick at the new dimensions that we're able to fabricate now. So fundamentally how this works is real simple. We apply a voltage, we apply a voltage from here to here. It's called a bias voltage. We have to put a voltage on. You saw on the FPGA, when we do the FPGA designs, we have to put a VCC on some of the inputs. That's equivalent to a bias voltage, which you don't see because it's already built into the FPGA schematic capture process. But you have to bias the transistor with a voltage. You have to give it a voltage. So we have to apply a voltage from here to here. Then all we have to do is apply a voltage here, and when we do that, we draw electrons from the p-type substrate up in this channel region. And look what we're doing now. We're literally closing the gap from here to here, and therefore allowing current to flow. And we've just turned our switch on. So this N-type transistor works by applying a positive voltage to the gate. With no voltage, no current flows. With a voltage, current flows. Okay? Now, the P-type transistor works completely opposite of that. Completely opposite. Instead of a N-type substrate, we have to use instead of a P-type substrate, we have to use an N-type substrate. Well, how do you put an N-type substrate in a P-doped silicon wafer? Well, we have to create a very special well. And so we create a very special well. We create an N+ well, an N-doped well by implanting in the silicon wafer. And then these become P+. Now we've got a P-type field effect transistor. But unlike an N-type transistor, in order to turn this one on, we don't have to apply any voltage. No voltage, and the device is already on. If we want to turn it off, we have to apply a voltage. So this works exactly opposite than the N-type. And Frank Longmas, engineer in the early 60s, took that idea to a whole new level. He created what we now call CMOS, which is the most dominant, prevalent chip design process we use around the world. It's the most dominant. And this is what he did. He basically connected two transistors together, a P-type and an N-type. And I talked a little bit about this, I think, yesterday. We talked about when radiation affects these, why does radiation cause these to leak, and this is why. So basically what he came up with was, he connected both of these together, a P-type and an N-type, and called that, because of their complementary nature, he called it complementary metal oxide semiconductor. And it works exactly like we just learned. If I have a 0 volts here, one of these is on and one of these is off. If I have 0 volts, which one is on? Right, the P-type is on, and this one's off. So essentially what I'm doing is I'm connecting my load out here, whatever it may be, to VCC, or VDD, the voltage. If I turn this on, if I apply a voltage here, or give it a logic 1 of these is on and one of these is off. Which one's on? The bottom one, the N-type. So now I'm driving this to ground. So I'm turning the output voltage off. So I'm always turning one of these on and one of these off. They're always one on, one off, always. What radiation does is in that junction I showed you earlier, if this is your junction on your transistor and P-doped material with N+ wells, this is your oxide, this is your gate. A couple of things will cause recombination in that channel region. This is called the channel region. And a couple of other things besides a voltage here will cause electrons to be attracted and therefore cause recombination. And two things that cause that to happen is external light or photons falling on that junction, or radiation. What radiation does is induces whole electron pairs and thereby turns this device on. It will turn it on when it's not supposed to be on. And this is what happens in a CMOS device. these both turn on at the same time, which is something you never want to happen. When you turn these both on, what you're essentially doing is creating a circuit of current path from power to ground, and your power level goes up. And another interesting thing about CMOS logic, in a static state, when it's not switching, it consumes almost no power because of the field effect design. But as you start switching it, the faster you switch it, it starts consuming more and more power. In fact, the relationship between frequency and power, between power, the power consumption is CV squared F. The power consumption of a CMOS circuit is equal to CV squared F, where F is the frequency. And you can see that the higher the frequency, like around 2, 3, 4 gigs, this thing's going to start consuming all kinds of power, which is now why we have to begin to cool these processors with a fan or some cooling method. This is why, because of the power consumption in higher frequencies. So that's basically the phenomenon. Now let's look and see how we actually fabricate these. We start with a molten silicon crucible. We literally melt pieces of silicon, purified silicon, in this big molten crucible. And as I mentioned yesterday, we lower a rod with either boron, typically boron, because we want it p-doped, into the bath, and then remove it slowly. And we draw from that what we call a boule, which is now a solid version of the purified, highly doped, purified silicon. And that boule looks something like this. Now nowadays, they stand about over 10 feet tall. We'll see one in a minute on a video. We turn that on its side, and we slice it into very thin silicon wafers. And then it's that wafer on which we imprint or implant or build these individual transistors. And the goal being now basically how many transistors can we fit on a piece of silicon in a tiny little square on this wafer, a square about the size of your fingernail. And we take that process to a whole new level now, because what we end up doing is we then want to build the microchips on that wafer, and we do that starting with a process known as photolithography. It actually starts with a design of the chip, which is what you see here. These are some of my early designs from some of my earlier designs on the wall. Those are actually millions and millions of transistors from different circuits that I designed, and we shrink those down, and through a series of steps, place masks over the wafer and either add stuff, remove stuff, implant stuff, or grow stuff. Those are the 4 processes. That turns into a microchip. We dice these up into many small pieces, place them into a package, and thereby creating our microchip. Let's watch a short video on this very process, and it gives you a better sense of what really goes on. You'll see these engineers are wearing these white suits in the laboratory, in the manufacturing plant, just because of dust and contaminants, and otherwise would just wreak havoc on these chips during the fabrication process. So let me bring up we're going to watch a video. It's just a few minutes long. It's about 5 minutes, or it's actually about 8 minutes actually, and show you exactly what goes on.
But we're surrounded by arguably the greatest, most revolutionary invention of the last 50 years. It's in TVs, stereos, watches, cars, phones, traffic lights, and pretty much every appliance in your kitchen. In fact, these days if a device uses electricity, it probably uses one. The tiny gizmo in question is, of course, the silicon chip.
Okay, hold on a second. This is the wrong video. This is the longer version of it, not the one I want. Give me 1 second here. I'll just show you the one we've been watching. It's got a little bit different tint to it. It's the same video, just short.
You may not realize it, but we're surrounded by arguably the greatest, most revolutionary invention of the last 50 years. It's in TVs, stereos, watches, cars, phones, traffic lights, and pretty well every appliance in your kitchen. In fact, these days, if a device uses electricity, it probably uses one. The tiny gizmo in question is, of course, the silicon chip. Making these extraordinary miniature electronic brains is one of the most complex manufacturing tasks ever attempted. So how do they do it? Texas, USA. Home to big stuff. Big cows, big boots, big hats, big moustaches. But Texas is also the birthplace of a miniaturized miracle, the silicon chip. And here in Sherman, 30 kilometers north of Dallas, is the MEMC Fabrication Facility. Here in this strange, futuristic-looking plant, they produce silicon wafers, which are the basis for all modern microchips. Silicon has special properties because it's what's called a semiconductor. That means, depending on how it's treated, silicon can either conduct or block the flow of electricity. It's this property that makes it perfect for supporting the millions of tiny transistors necessary for a modern computer chip. The trouble is, because these transistors are so incredibly small, the silicon base on which they rest needs to be absolutely perfect. It took decades to discover a way to produce silicon with a perfect monocrystalline structure. They begin with raw polysilicon, or poly, and heat it to 1420 degrees Celsius inside a special sealed furnace, which has been purged with argon gas to eliminate any air. The resulting lake of molten silicon is then spun in a crucible, and a silicon seed crystal, roughly the size and shape of a pencil, is lowered into it while spinning in the opposite direction. As the molten polysilicon is allowed to cool, the seed crystal is slowly withdrawn at around 1.5 millimeters a minute. The result is a single silicon crystal weighing around 200 kilos and with a diameter of around 200 millimeters. The crystal is so strong, its entire weight can be supported by a single thread just 3 millimeters across. But it is brittle, and it must now be cut down to size without shattering. So after testing with chemicals and X-rays to check its purity and molecular orientation, it's fed to a silicon salami slicer. This 10-ton wire saw uses a fast-moving web of ultra-thin wire to produce wafers of silicon that are just 2/3 of a millimeter thick and 99.999999% pure. But once cut, there are microscopic marks left on the wafer's surface. So it's time for a buff-up using a process called lapping. But even after a twirl in this high-powered polisher, they're still not smooth enough. So they're then given yet another buff using a chemical process. The result is wafers of silicon with a surface roughness of less than 0.1 billion billionths of a meter. Buffed to a sheen, they're now ready for etching with the circuit design. Packing millions of transistors onto these tiny wafers is the job of chip manufacturers like Texas Instruments. Back in 1958, the inventor of the integrated circuit, Jack Kilby, managed to squeeze a single transistor onto his design. These days, the latest generation use almost 1 billion, and according to Moore's law, that number doubles every 2 years. But of course, the more they try and pack into the design, the smaller each transistor needs to get.
There are over 250 million transistors in this design. Someone has to shrink them down to this.
Working at this microscopic scale exposes the chip makers to a major problem. When a transistor is only 1/10,000th of a millimeter across, the smallest particle of dust is enough to cause an electronic train wreck. So, before staff like Dame Bailey set to work in the fab, it's on with the bunny suit.
Wafer Fab stands for Wafer Fabrication. We build the chips here. We start with the bare silicon wafer. We run through a multitude of different processing steps. For our general product that we make here, a DSP, typically takes on the order of about 1,500 individual processing steps from start to finish.
With an area of just under 18,000 square meters, the fab is a Class 1 clean room. Thanks to 12,000 tons of air conditioning equipment, the air is 1,000 times cleaner than a hospital operating theatre.
There's actually less than 100 particles per cubic foot of air. As few as one particle landing on a critical area can kill a chip.
To give you an idea how clean this room is, walking alone produces 5 million particles every minute. So, to avoid contamination from the inadvertently dusty staff, front-opening unified pods, or FOUPs, ferry packets of wafers through the intricate process of component construction. The key problem is miniaturizing the complex designs and imprinting them on the wafers. It's done through a process known as photolithography. First, the wafer is coated with photosensitive chemicals, which harden when exposed to UV light. In sealed darkrooms, light is shone through an image of the design, then through a miniaturizing lens and onto the coated wafer. When the chemical is washed off, the design remains, just like a developed photographic image. But in order to pack all the components onto the wafer, they're built up layer by layer, like floors in a miniature skyscraper. So to complete the job, the FOUPs cycle the wafers up to 40 times, repeating the photo-etching process for each new layer. Some layers are cooked, some blasted with ionized plasma, some bathed in metals. Each different type of treatment changes the properties for that layer and slowly forms part of the jigsaw making up the chip's design. The finished sheets of silicon wafer carry up to 1,000 individual microchips and over 4,000 billion circuit elements. All that remains is to slice and dice, and the journey from sand to circuit board is complete. What was once a worthless pile of sand can now change hands for more than $17,000 a gram and calculate pi to 1,000 decimal places in the blink of an eye. Metaphysical poet William Blake reckoned he could see a world in a grain of sand. But if he were to look again now, he would surely be even more amazed to discover 1 billion tiny transistors.
Okay, thank you. So you got a good sense of what goes on now. This is basically the manufacturing process of every microprocessor, every chip on the planet Earth today. More or less 99% of them. And just to give you kind of a sense of what we're talking about, in the early days we actually started fabricating, drawing, just like you saw, drawing from a bowl, a 3-inch ingot. This is actually a silicon wafer that was taken from a 3-inch ingot, sawn, cut like a piece of salami, polished, and then fabricated through photolithography processes. the actual microchip designs on the surface of the chip, of the wafer. We dice these up, we place them in a package, and we end up with, in the early days, microchips that looked a lot like this. These are just hundreds and many different kinds of early microchips, that all of which have a small chip inside of the package designed primarily just for handling purposes. We would then take this microchip, place it on a board, and now there's your product. There's your motherboard, there's your PC board, there's basically your design. And today, this process is repeated even to this day with even devices like your smartphone, your computers, your routers, what have you. Now, these weren't the only sizes that we were able to manufacture. Certainly not limiting to 3 inches. As you saw in the photograph, we actually were able to fabricate now on silicon wafers that were 6 inches in diameter. And the diameter is really just a function of the size of the bowl that we pull from the crucible. And you can see those are all identical, just like baking cookies. You don't bake one cookie, you bake many of them. You plot them all down, pop them all down, and saw them off. And this process became, of course, more refined and more mature. And by no means were we limited to 6 inches. We're now able to create and fabricate a lot of microchips in a small area of these. This is an 8-inch wafer. I don't know if you can see from where you are. I'm going to come back there and show you how many actual chips we have on this surface. There are probably thousands on this particular silicon wafer. This is a P-doped wafer, just like we talked about. And you can see there are literally thousands, perhaps, of small integrated circuits on this one wafer. These are all identical with the same exact part because we basically replicate them just like we bake cookies. And we saw these off and placed them in a small package, and we end up now with thousands of products. And you can see the benefit here is to manufacture on as big a wafer as we can, but with as small a chip design as humanly possible or as necessary. I mean, you can build these at all different shapes and sizes. These are all 8-inch wafers, and these all have different size chips on them. So the ratio is of course going to be to maximize the wafer size and minimize the chip size. And by no means are we restricted to doing this to 8-inch wafers alone. In fact, right now the most common wafer size is not 8 inches, but rather 12 inches. This is a 12-inch P-doped silicon wafer, manufactured exactly like you just saw. We just drew it from a 12-inch crucible, and we're able to pull it as a bowl from that process. This is an unprocessed wafer, which means we haven't yet gone through the photolithographic process and built the actual transistors on here. But we're literally now able to build microchips with as many as 7 to 10 billion transistors on them, individual P-type and N-type transistors on a piece of silicon about the size of your fingernail. That's the magnitude. So I ask you this question: which do you think would be more complicated to build? A complex microchip today or an Airbus A380? I think the answer is a microchip. And the reason is because of the numerous fine dimensions that we have to achieve. And these dimensions, by the way, that channel region that you saw that I drew up there, the typical channel region now on today's chips is roughly on the order of about 7 nanometers. 7 nanometers with oxide thicknesses down around 1 or 2 atoms thick. Now measuring those incredibly fine dimensions is an extraordinary process in itself. And by the way, do you think we're technically limited to 12-inch wafers? No. Why? We don't build 18-inch wafers, but we could. Why don't we? Expensive. What? Expensive. It's a fundamental matter of economics. It just isn't cost effective. But we are clearly capable of building right now 18-inch wafers. And I think there's been some experimentation done. It's just a much bigger wafer. Today's foundries cost about $10 billion to build. And the cost of building a new foundry to support an 18-inch wafer just simply yet is not cost effective. So that's pretty much how we build microchips. And in fact, if you guys come over here, I'll show you something really cool. When I built these microchips, I actually inscribed something on the silicon, on gold. I wrote a couple little messages to my daughters on these microchips that we just today, for the first time, I know what they say, but we only are now, for the first time, able to actually see them because we have a microscope that allows us to see them. So if you want to see what it says, what you got to do is you got to hold this green light, and this isn't going to hurt you. It's just a green monochromatic light source. But if you hold it just right on the wafer, on the chip rather, let me see if I can get it. There we go. And you zoom in just right. Now, for some reason I can't see it now. Oh, there it is. Okay. Now, don't touch it because you'll move it, because it's at a fairly high magnification. But if you look in there and hold this just right, and again, it's a class 3, it's not going to hurt you. You got to hold it in the right angle for it to reflect the letters. You'll see several rows of letters that I wrote to my daughters. This is a message I wrote to my daughters for them so that one day would look at this and you can have a seat if it's more convenient. What you want to do is you want to just take the light and shine it around there so that you get an image here in the lens. And if you might want to sit if you're more comfortable to be more stable. And hold your hand. Maybe hold your hand against the microscope so it doesn't move. You're a lot more. You're light hand. Here, actually, you know what? Why don't I do it? I'll tell you. I'll hold the light, and you tell me when.
Yes. Wait. Go back and reword. Yeah, I see.
You see the letters?
Yeah.
You see what it says? Can you read it?
Athens, HMA, Lima, Basile, 2002.
Right. That's exactly it. And those are encrypted messages from my daughters that I hope that they'll see someday. If you're seeing it for the first time, tell me when.
Athens. No, go down a little. Wait.
There?
Oh yeah, I see it. How did you engrave that?
Well, I laid it down just like we laid the silicon. Remember I told you we add stuff, we remove stuff, we grow stuff, and we implant? I added those letters in gold with a mask, just like I would a chip. It thinks those just appear to be conductor lines. It doesn't matter. That's exactly what I did. Tell me when. You see it? Did the letters come out? Can you see the letters? Okay. Tell me. You may have to focus it. If you have to focus it, go ahead and focus it because you got. We have different. There you go. Tell me if the light's okay. Oh, you see it. Wow.
H-E-N.
Right. That's great.
2010.
Cool. They're gonna love it. My daughters are gonna love this when they hear you guys read what you're reading because they know what it means. You might have to focus it if it's not in focus. Can you see it?
I don't see any further. Oh, wait.
I'll move it around. Tell me when. See it?
Not yet. Oh, wait. Go back to where you were before. I see you.
There?
Yeah, I can't really see it.
Okay, it's just because I don't have the light. Let me try it over here.
Oh, I see it. Oh, I saw it for a second.
There?
No, angle it a bit to the left, maybe.
There? Tell me when.
A little to the left. Can't get it right.
See?
Oh, I see it a bit.
There?
Yeah, I just can't focus.
Go ahead and turn the knob to focus it. This knob here. Here, this one here. Yeah, that'll focus. Let me try to get back where I was. Got it?
Up. Right about there. Yes, I can see it.
Okay, cool.
Yeah.
All right. Now those letters are obviously very small dimensions. They have to be. And it only takes a microscope. You're only able to see it with a microscope. So that's actually, this is actually one of my many chips that I had developed. It's in a package. And these are some of the chips that I have used in my research and experimented with at the integrated level. In fact, Daniel, in answer to your question yesterday, this is the chip I developed to demonstrate a method of recovering from radiation effects in space. Space radiation it wreaks havoc on microelectronics, and one of my inventions from one of my patents actually describes a method to overcome that effect. And we tried to get that actually qualified on a space mission to Jupiter many years ago. We tried to present that material to jet propulsion labs and attempted to get that technology qualified. It didn't get qualified, but the technology that got qualified was similar to this from a different company. In fact, the company was called Aeroflex. And it was their technology that I think was subsequently qualified for that mission. So that's it. That's pretty much it. That's our presentation. And any questions? You guys have any questions? Okay, with that, we'll go ahead and take a break.